Hello students, in lecture 7 of your course Advanced Calculus and Special Function, we discuss certain examples related to partial derivative of composite functions, second order partial derivatives, directional derivatives, and change in order of partial derivative. So first we consider certain examples related to composite function. Here you see this example 1. You are given z is a function of x and y. Then prove that if x is equal to this and y equal to this expression, then you have to prove that this del z over del u minus del z over del v is equal to x into del z over del x minus y del z over del y. Means you have to prove this left hand side is equal to right hand side. So we start the solution here. Here we look upon z as a composite function of u and b. Here you can see that you are given z is a function of x and y. And further, you are given here, you can see that x is a function of two variables u and v. That means x is further a function of two variables u and v. Similarly, y is also a function of two variables u and v. So we can say that z is a function of x and y, and further this x is a function of u and v. Similarly, y is a function of u and v. So as explained in the last lecture, the partial derivative of z with respect to this variable u can be obtained using this formula. The del z over del u is equal to del z over del x into del x over del u plus del z over del y into del y over del u. Exactly in the same manner, if we want to find the partial derivative of z with respect to v, we can find in this manner. That can be calculated in this way, that del z over del v is equal to this expression here, del z over del x dot del x over del v, this thing and this thing. So now from these expressions, suppose I say that this is let us put the values first here. Here you can see that del z over del x cannot be calculated here. It can be kept in the same form as it is. Why? Because here we are given z is a function of x and y. That means we are given z is a function of x and y. Simply, we are not given that z equal to something x square plus y square or z equal to xy. Means this is not given to be a fixed expression. In fact, it is a general form. That is why we are keeping this del z over del x as such here. But we can evaluate this del x over del u. How? Because you are given x as a function of u and v. And you can see when you are given x is equal to e raised to power u plus e raised to power minus v, then del x over del u is equal to e raised to power u, because the second variable will be treated as a constant, and with therefore the derivative of the second part is 0. So in fact you are getting del x over del u is equal to e raised to power u. So that you are substituting over here. Similarly, here if you check it, del z over del y will be kept as such, and you calculate del y over del u. That means you take the partial derivative of this with respect to u, you will get minus of e raised to power minus u. So the minus sign is here. So that way you are getting this expression. Now let I say that this is equation 1. exactly in the same manner, we evaluate the value of del z over del v, and suppose this equation is number 2. Now we want to have the value of del z over del u and del minus del z over del v. So what we should do over here, we should subtract equation 2 from equation 1. So the left hand side will appear del z over del x minus del z over del v, and let us see what happens in the right hand side. So on subtracting, the left hand side becomes this and right hand side becomes this. But from the given expressions, you know this is given to be x, this quantity, and this quantity is given to be y. So you are writing here x del z over del x minus y. In place of this, you are writing x here minus this thing as such, and in place of this, you are writing y here. So you have proved that this quantity is equal to this quantity. That means that left hand side is equal to right hand side. So we have proved the desired result. Now we see this example number 2. Here we are given that h is a function of y minus z, z minus x, and x minus y. Then prove that del h over del x plus del h over del y plus del h over del z equal to 0. So how to prove this? We solve this here. We take u equal to this quantity y minus z. We cannot leave this function as it is y, because here f is not given to be a function of x or y or z. So actually this within this f is a function of certain expressions in terms of x, y, and z. So let us assume this expression is equal to something, this expression is equal to something, and this expression is equal to something. So we are taking this expression is equal to u. That means this expression is giving you a variable u, and this expression is giving you a variable v. Definitely these two are variable. That is why this is a variable. Exactly in the same manner, u is a variable. And similarly for the third case, this x minus y, you substitute it equal to w, then w is also a variable. Consequently, this h becomes a function of u, v, and w. Now let us look at these variables u, v, and w. In fact, this u can be written as 0 into x plus y minus z, and this v can be written as 0 into y plus z minus x, because 0 multiply y will give you 0, and the same thing is left over here. And in the same manner, you can write here 0 into z plus x minus y. We are showing here z and here y and here x, so that all of these three variables u, v, and w will look will be appearing as function of three variables x, y, and z. Now from this type of interpretation, we can consider u as a function of three variables x, y, and z. Similarly, this v can also be considered as a function of three variables x, y, and z. And again, w is also a function of three variables x, y, and z. Now see what happens. Now you can see that h is a function. Here you can see this h is a function of three variables u, v, and w. And each of these three variables are further functions of suppose this is function of x, y, and z, and this is again a function of x, y, and z, and this is again some function of x, y, and z. So I can say that this h is composite function of x, y, and z. So here, as we have done in the first example, here we can find three derivatives, partial derivatives due to this composite function of x, y, and z. we can find this. We can find curly h by curly y, or del h by del y, then del h over del z. So the formula of this, as we have already discussed, will appear in this form: del h by del x is equal to del h by del u, because we will consider all these three: del h by del u, then del u by del x, del h by del v by del x, del h by del w, and del w by del x. Now, as in earlier case, h is simply is not a fixed expression, but is given to be a general function of u, v, and w. So we cannot evaluate the exact value of this del h over del u. So it will be left as such. We can evaluate value of del u by del xy, because you are given u is equal to, here it was given u is equal to y minus z. So you can write here y u equal to y minus z, and similarly, so you can find here del u by del x is in fact 0, because there is no x. So you write here value of del u by del x equal to 0. So this del h by del v will be left as such. Del v by del x will be minus 1. Del h by del w will be as such, and del w by del x equal to 1. So therefore, this expression del h by del x gives you this thing. That means you are having del h by del x is equal to this thing. Exactly following the same steps, we can get del h by del y equal to this quantity. Let this is number 2, and del h by del z this quantity. Let this is number 3. Adding all these, you can get in left hand side that del h by del x plus del h by del y and del h by del z, and right hand side, when you add all the these terms will be cancelled out, and we will get the desired result. So this is the exercise. Based on these, you can try this regarding the for finding the composite function. So next topic is the directional derivative. What is the meaning of directional derivative of a function? You know, if we have a function of two variables, then a function of two variables represents a surface. Usually we find the directional derivative at a point. Suppose you are given a function z of two variables x, y. In fact, in vector notation, this xy can simply be written as f. This is bold x. In fact, this is vector x. This x means this pair xy. That is why we are representing here function. The surface is represented by this function. In fact, this is not the single variable. In fact, it is an ordered pair like this xy, due to two variables x and y. So now, if this is the point x naught, and let the two coordinate of this point x naught are x, y. X variable is x and y is y here. Now we want to find the directional derivative of this function at this point. The definition of directional derivative is that it represents the rate of change of a function along a given direction. Rate of change of a function along a given direction. And you know, a direction is identified by a unit vector. For example, when we have three-dimensional coordinate system, that is x-axis, y-axis, and z-axis, the unit vector in direction of x-axis is I cap, in direction of y-axis is j cap, and direction of z-axis is k cap. So if we are saying that we want to find the directional derivative along x-axis, that means you will say that you are finding the directional derivative along the unit vector I cap. So let us interpret this situation in another way. You want to find the directional derivative at this point x naught here as shown in the figure here. So we have x naught equal to xy, and suppose we are taking unit vector u as 1 0 in vector form, and if we write in this type of representation, you can write 1 dot I cap 1 into I cap plus 0 into j cap, and you can see the magnitude of this u is 1, so you can say this u is a unit vector, and in fact here u is I cap, unit vector along x-axis. Now we define the directional derivative here in this way. D derivative means direct, capital D stands for the directional derivative in the direction of this unit vector u at a point x naught, means here, is equal to limit h tending to 0 f of x naught plus h u is the unit vector here minus f of x naught. Now let us think about this situation. What does it mean? In fact, here x naught is not a single number, but it is in two dimensions here. It will be having two coordinates x naught and this x and y. So in place of this x naught, we can write f of xy plus h as such here, and then in place of you see here in place of this u we can write 1 0 because u is 1 0 minus f of x naught, we can write f of x y, fine, divided by h, limit h tending to 0. Now you can see when you multiply h inside, it will be h comma 0, and now these are two vectors xy plus h comma 0, and then you add these, you will get here f of x plus h, means the first element will be added to first one and second from to second. So we will be getting limit h tending to 0 f of x plus h comma y minus f of x y divided by h. Now what is the meaning of this? In case of two variables, what does this expression represent? This represents the partial derivative of f with respect to x. So you can say that here we have obtained that this du f at the point x naught is in fact the partial derivative of f with respect to x. Partial derivative of f with respect to x if the unit vector here u is I cap, that means if you are assuming the direction along x-axis. So the first partial derivative represents the directional derivative along the x-axis. Similarly, if we consider here j, so this, suppose this becomes v and we write 0 1, so here will be to j, so that way it will become del f over del y, means the first order partial derivative of the function f with respect to y will represent the rate of change of the function along the direction of y axis. So these are two you say in rectangular coordinates, these are two directions, perpendicular directions along x-axis and y-axis, but in general it is not that you will be seeing the change only along the x-axis and the y-axis, means in general you can have any direction, and that direction you can say can be anywhere, and that will be represented by a unit vector. That is why here a general unit vector u is considered, because if you consider that this is the direction here. So now we extend this idea for function of more than more than two variables. In general, we can say again the notion of repeating here for this thing. The notion of partial derivative can easily be generalized to a directional derivative, which measures the rate of change of function at a point along a given direction. Suppose we specify the direction by specifying a unit vector. Okay, so it is not always that, as I have considered here, that it is along x-axis, it will be I 0 j, that means 1 0, but we can also have a unit vector for which you will be having both the components I and j. For example, I talk about such a unit vector. I can assume u equal to cos theta sine theta. Means I can assume u equal to cos theta I cap plus sine theta j cap. Then you can see that magnitude of this will be 1. So this u is a unit vector and none of the component is 0. So in that situation, you can say that this is something u1 and this is something u2. So a unit vector can be represented by two non-zero components u1 and u2. So in that situation, how the directional derivative will be defined. So keeping in view this fact, we specify, as I have already mentioned, that the direction will be specified with the help of a unit vector. We specify a direction by a unit vector. Let u equal to u1 u2. U is identified with these two components, be a unit vector in R square. R square means the two-dimensional plane where this is a real line and this is a real line. So any point here u, this point unit vector is in this direction, whose components are means u1 I cap and u2 j cap. Suppose this is the situation. So u1 square plus u2 square will be 1. Also, suppose you are taking any subset of R square and a function f d to R be a function. Let x0 y0 belong to D, means you want to find the change at this point, and let this is denoted by u0. This point is denoted by u0. So D contains a segment of line through x0 y0 in the direction of u, because at the point wherever you want to find the directional derivative, definitely that point would be lying on the unit vector along which you want to find the change. This is the first requirement here. We cannot find here, if direction is like this, then we cannot find the directional derivative at this, because we can find the directional derivative on a point if it is lying on the unit vector. So here we can say that the point inside this region D is any subset of R square. Any segment in this will be given by this factor, and any point here will be given by this x0 plus tu1 y0 plus tu2 that belongs to D. We define the directional derivative of f at the point this along u as follows. In the earlier case, I have taken the small step along x-axis or along y-axis, that was h. Along x-axis I have discussed here, that was h. But here we are taking the step along x and y, because now we are neither moving along x-axis nor y-axis. We are moving somewhere else. So when we are moving along some other direction, then we are moving along x as well as along y. So that is why we are adding this t to both the components, x0 plus tu0, y0 plus tu2, and tu1 and y0 plus tu2, this thing, provided these limits exist. So this is denoted by du of f at x0 y0. Now if v equal to minus u, then you can have dv f of x0 is equal to minus du f of x not y0. Note that, as I have already discussed in earlier slide, that I equal to 1 0, I can be written like this, j can be written like this, and this dif becomes the first order partial derivative, means fx curly f by curly x, and this becomes this curly f over curly y. So this is the concept of partial directional derivative. Now come to the second order partial derivative. Second order partial derivatives, if we have a function of two variables z as function of two variables, if you differentiate partially with respect to x, you get del z by del x, and you further differentiate the expression with respect to x partially, you get del square z over del x square. Similarly, del square z over del y square. Now, these are the mixed partials or mixed partial derivatives. When you differentiate this one with respect to y, we get del square z, del y, del x. Also, when del z over del y is differentiated partially with respect to x, we get this. So, these two may be equal or may not be equal. If two mixed second order partial derivatives are continuous, then they have to be equal. The condition is that if this is continuous function and this is a continuous function, then they will be equal, but they may not be equal. There are situations of circumstances where these are not equal, so that we are going to discuss in the subsequent lecture. You have next example here, the first part. Let you have a function from r square to r given by f of x y equal to x square y plus x y square, and you have a point x naught y naught belong to r square. You take the first order partial derivative of this with respect to x, and then put the coordinate of certain point x naught y naught, we get this thing. Similarly, we can find fy at x naught y naught point, that is equal to this thing. Consequently, the second order derivative at the same point comes out to be this, and this comes out to be this. Now let us look at the mixed partial order derivatives. Mixed partials means we want to find f of xy and f of yx. So you will observe that if you find f of xy, that will be the same thing, and if you find this fyx, that will be the same thing. So this is the special case here, because the expression is continuous function because it is a polynomial, and a polynomial function is always a continuous function. That is why this f of xy or fyx, that is mixed partials, are equal. Now the second case, we have this fr square to r given by f of xy equal to sin xy, and we have any point x naught y naught belong to r square. We find first order partial derivative is this with respect to x, and with respect to y is this, and consequently you find second order derivative fxx is this quantity, fyy is this quantity, then you find fxy and fyx, they are also found to be equal. So in the example above given here, the mixed partial turned out to be equal. Presently, we will show that this is always the case whenever the first order partial derivatives exist and one of the mixed second order partial derivative is continuous. So you can see the situation. We have this proposition 1, suppose, and this is called the mixed partial theorems. We write here, let D is any subset of R square be an open set, and let x naught y naught, this is any point in the domain D, or then we have a function, let we have a function f d to R such that both first order partial derivatives fx and fy exist on D, means at every point of the set D, this fx and fy exist, both exist, and continuous at certain point x naught y naught, and suppose these are continuous at some point, this x naught y naught, both are continuous, then both the partial derivatives fxy and second order partial derivatives fxy and fyx exist, and they will be equal, So what is this proposition says? It says that in order to these two mixed partial second order partials be equal, that this condition must be satisfied. What is the condition? These first order partial derivatives must exist at this point, and these must be continuous. This fxy or one of these, f of xy or f of yx, one of these exist in D and continuous at this point. Means both of these two first order partial derivatives must exist at this point, and these must exist on the whole domain, and at the point x0 y0 one of these must exist, and one then we can say that fxy at x0 y0 will be equal to fyx at x0 y0. You can see this example. In this example you can see that f of r square to r be given by this one, this expression when xy not equal to 0 0 and equal to 0 if xy equal to 0 0. It is clear that the first order partial derivative fx fy exist on the whole domain, except yeah, it will exist on the whole domain. We can find fx as well as fy because it would not be existing at 0 0, but the function is defined here that this quantity is 0 whenever xy equal to 0 0, and you can find the first order derivative of 0. So you can say fx and fy exist on the whole domain, and you see if you find fxy and fyx, they also exist on r square minus 0 0. They also exist on, this stands for minus, r square minus 0 0. It is easy to see that fx, if you find the first order derivative and you put x naught equal to 0, we get minus y naught. And if we find fy naught at x naught and we are taking y naught equal to 0, that is equal to x naught. So hence we can say that fxy at 0 0, fxy at 0 0 is equal to minus 1, but fyx at 0 0 equal to 1, means they are not equal. Therefore from this proposition 1, the result of this proposition 1, it follows that neither fx nor fy can be continuous at 0 0. So this is a this example, the result of this example is followed from this proposition 1. Now next is the change in the order of partial derivatives. Again we are focusing on the same fact as in this proposition, so more elaborately we are going to discuss the things. In most of the cases that occurs in practice, a partial derivative has the same value in whatever order the different operations are performed. Thus, for example, it is usually found that f of xy equal to fyx. And one is often tempted to believe that it is always so. But it is not the case. There is no priori reason why they should be equal. Let us now see fxy may be different from fyx, as we have seen in the last example, at some point a b of a region. Now we have this fxy can be written as, in fact here they are writing, they are keeping the first, they are finding the partial derivative with respect to y then x. Actually notation is like that in this situation, and here fy plus h means we are changing the x variable. That is why we are taking the derivative, partial derivative of fy with respect to x. So the notation here is written like this: f of xy ab equal to this quantity. Similarly, now here we open this. What is meaning of this and what is meaning of this? Let us see. So these two things, and we are keeping 1 by h outside. You can see 1 by h is outside, limit k tending to 0, because that was the partial derivative with respect to y. That means there was change in the variable y. B plus k, f of a plus h b will be kept as such and divided by k, limit k tend to 0. Similarly for the second part. This part can be expanded in this manner. So now we are having these consecutive limits, limit h tend to 0, limit k tend to 0, this expression is left with. Now in this expression we are taking the limit h tending to 0, k tending to 0. The whole expression in the numerator can be written as phi of hk, and in denominator this is h into k, h into k. So where phi hk equal to this quantity and limit h tend to 0 and k tending to 0. Similarly, when we find fyx, it gives you limit s k tending to 0, h tending to 0. That means this one and this one both are same expression, but with the change in the order of the limits. So there is no reason that we can say that these repeated limits s tending to 0, k tending to 0, or if we take k tending to 0, s tending to 0, that they will always be equal. It is there is no such a fixed rule, so they can be different. So that is why we say that the mixed partials, in fact this fxy at some point ab, may or may not be, may or may not be equal to fyx ab. So next example, that is the conclusion here. Examine the equality of fxy, fyx for this function. So you can check, this is x cube y plus e raised to power xy square. So you can verify. Then in this case, what is happening, whether these are equal or not. Next example, suppose you take fxy equal to this quantity when xy not equal to 0, 0, and this is equal to 0 when this one. So here we find, in fact this is the same example, yeah, this one, this is the same example. So another way you can see the proof of this, we will show here that they are not equal at origin. Fxy at 0, 0 can be written like this by the definition. Similarly, fy 0, 0, this fy 0, 0, this one can be written like this, and this fy h0 can be written like this. By substituting the values over here, we get that this quantity fxy will be equal to limit h tending to 0, and substituting the values h minus 0 divided by s, this gives you 1. Means the value of this fxy at 0, 0 comes out to be 1. Next we find the value of fyx at 0, 0. We will see that it comes out to be minus 1. So they are not equal. So in fact that this is the same example which we have earlier discussed, and in more elaborative form. Now this is the exercise for your practice. Examine the change in order of derivation at the origin for each of the function. Means you have to, in fact, in all these three problems, what you are going to check, you will going to check f of xy at 0, 0 and f of this at yx at 0, 0, whether these two are equal or not, for all these three problems you can see. So that's it for this lecture, and most of the content we have consulted from this book, S.C. Malik. Thank you.